everyone. I think thank you. A few more people will be kind of trickling in, but welcome to the Statistical Methods for Health Equity webinar series. And so this month, this is a monthly webinar series focusing on statistical and machine learning methods that have the potential to promote health equity. For example, methods that can shed light on the complex factors underlying health inequalities, or fairer algorithms can appropriately take into account the biases that exist in biomedical data sets. This series is co-hosted by the Alan Turing Institute, specifically the Health Equity Interest Group, the UCL Statistical Science Department, and the Data Science for Health Equity community, also called DISHI. And DISHI is a community of experts and enthusiasts working at the intersection of data science and health inequalities. And DISHI's aim is to ensure that the latest research and innovations in data science, machine learning, and AI improves everyone's health, especially those in underserved populations. If this sounds like something you're interested in, I will post some stuff in the chat of different ways you can get involved. And today it is my great pleasure to welcome Briana Stephenson. I even just checked that and I'm still going to pronounce it wrong. Is an Assistant Professor of Biostatistics at the Harvard T.H. Chan School of Public Health. And I will hand it over to her to introduce her talk. As usual, if you have any questions, there'll be time for discussion at the end, or you can pop your messages in the chat. Thanks very much.
Thank you, Lizzie. Oh, shoot. Pleasure to be here. Yeah, so today's talk will be talking about the utility of mixture models to examine patterns of underserved populations. So this is a lot of the work that goes on in our lab. So we will start off. Okay, now I can't drive. There we go. Okay. So I'll start off by talking about the mixture model framework, which a lot of our research kind of stems from. We'll go through a combination of some new methods, but also some existing methods that we found great utility to kind of answer some interesting questions as it relates to this area. So first, we'll talk about dietary patterns for low-income adult populations. So much of my work deals with high-dimensional exposures. And so this exposure right here we're talking about is dietary intake, and we're focusing on low-income adult populations. And there's a couple of different methods that have come out of our lab with our student who just recently graduated, Dr. Wu, looking at Bayesian mixture models with survey data. Then we'll march over to neighborhood social determinants of health. And so this is an existing method. We're looking at the multivariate Bernoulli mixture model. So if anyone is familiar with the R package Bayes bin mix, we've had a lot of fun using that package to kind of answer some other interesting questions. And then we've done a combination of two different mixture models. So we were looking at the interrelationship of PFAS and dietary exposures in pregnant women. So this uses a combination of a Bayesian repulsive Gaussian mixture model, as well as the robust profile clustering model. And then we'll talk about some other stuff that's going on that I probably will run out of time in getting to, but these are kind of the most recent works that we have done. Okay, so I tend to focus on populations in the United States. So the diversity that makes up the United States in 2020, the census confirmed that major changes in racial, ethnic, and demographic landscape have significantly increased from a decade ago. So in 2010, it was about 54.9, and in most recent 2020, it was up to 61.1%. So this increased population diversity really warrants a new study design and different methodological approaches to ensure that the inference that we're making about our data is equitable and applies to all residents in the United States. One of the things we want to think about is, how is the data going to influence public health, and does it reflect the population that we most want to serve? So oftentimes what we find in clinical trials and cohort studies, there's usually an overrepresentation of some demographic and an underrepresentation of another demographic. And so it often requires some new sampling strategies in how we're collecting data in order to increase and address this representation. So with those new sampling strategies also comes new methods to kind of resolve what's going on with our data. Okay, so how are we defining underserved populations? So underserved populations are often the populations that are overlooked in population research, and usually resulting in some sort of disparity for their overall health and well-being. So The Center for Disease Control defines health disparities as preventable differences in the burden of disease, injury, violence, or opportunities to achieve optimal health that are experienced by socially disadvantaged populations. So this could apply to different ancestries, race, ethnicity, socioeconomic status, sexual and gender identities, geographic locations. So oftentimes, some of the underrepresented populations we see are Puerto Rico, Guam, and also Alaska and Hawaii, just because they don't make up the contiguous United States. Rural locations, immigrants, refugees, asylum seekers, the elderly, young adults, and then individuals with disabilities, and those with a lack of health insurance coverage. Okay. So just want to make sure everybody's on the same page for those that have never used a mixture model. The mixture model framework is kind of made up of two components. So in the yellow, we have the probability that you're going to have some sort of pattern. You're going to exhibit some sort of pattern. And then we want to know what that pattern looks like. So that pattern that it looks like is going to be described in our green box to the right. So we tend to use a model-based clustering approach to identify these patterns to kind of give a probabilistic nature into what things might be shared within that population. And so the number of patterns we can kind of signify with K, which is our blue circle. So in our lab, we've kind of worked with a myriad of different distributions. So the focus is kind of on that left was a green box, now it's a blue box. That can make up many different distributions depending on the data that you're dealing with. And this can be univariate. So maybe you're just looking at differences that exist with one variable. However, in our lab, we work with many exposures, many different variables. So more in a high dimensional construct. So this is going to think more of like a multivariate distribution. So some of the distributions we have are beta, normal, Poisson, multinomial, gamma, and Bernoulli. I'm not going to have time to go through all the ways we've applied data for this, but we will highlight just a few. Okay, so switching gears, I mentioned how one of the ways that we're able to collect data on underserved populations is we can use what's called survey data. So this is a great opportunity to capture communities that are typically understudied, underrepresented, and hard to reach. And so a bunch of different methods are usually implicated. There's usually some sort of cluster sampling, some stratification. Oftentimes there's an oversampling of the population that we really want to get information on, and then some post-stratification and calibration. So you can see the little image that we have on the right. You know, you might start with this random county that you'll select, and then you'll kind of own in down until you get down to the individual. And each of those stages has its own different probability structure, as well as a sampling distribution. So with that comes some methodological challenges, right? So there's going to be some limited generalizability. Not everybody's going to respond to every survey. How I'm selecting someone to be chosen is not going to be equal because, as I mentioned, I might try to oversample a certain population I want to get more information on compared to other populations. So a lot of the standard methods that we use often used to rely on a simple random sampling scheme, but that is not what's being used for how we're collecting the data for those surveys. So with that, you're getting a lot of population heterogeneity and you're getting a little bit of sparsity with that non-response bias. And so it's going to require different methods for us to be able to use. So Dr. Stephanie Wu, who just graduated this past December, and rumor has it she'll be starting as a research scientist, at UCL very soon. We started to look at ways that we can incorporate Bayesian methods with survey data. So typically these two have not mixed together, and that's mainly because surveys are the way that their complex sampling design is organized. It relies on a frequentist sampling design. So frequentist and Bayesian used to be on two opposite ends of the spectrum, but I think with a lot of advanced computational tools, we've been able to figure out ways to kind of merge the two together. So Bayesian methods are really great for survey data, especially when we're talking about the heterogeneity that's going to exist within that population, and then the sparsity that might come from either non-response or, again, the oversampling of some demographics over another demographic. So if you look into the literature about what things have been used for Bayesian methods and survey data, they kind of fall into three different categories. So first, you'll have a multi-level regression and post-stratification. So basically what's happening here is you're taking your population, you're going to divide it into different samples, which you'll call post-stratification cells. And then within each of those strata, you're going to estimate the sample mean And then from there, you'll combine into some sort of method to get an overall mean population. The weighted pseudo likelihood approach is basically we're going to take each of these subjects and we're going to apply different weights. And this weights oftentimes is going to be based off of the way in which you were selected to join into this study. We'll build some sort of pseudo likelihood, so it almost looks like the population we wanted it to be. And then we'll do our parametric model off of that. And then the third option is a synthetic population generation. And so in this case, what we're doing is we're going to impute all of those units that were not originally sampled, and then we'll run an analysis in parallel for all of these different, almost like a bootstrap that we're doing, and we'll pull those estimates all together. So for this talk, I'll be focusing more on the weighted pseudo likelihood for some of the methods that we've created. So as I mentioned, our main application here is survey data to identify dietary patterns for marginalized population. Our marginalized population for this talk is going to focus on low-income adults. And so we're looking at diet because unhealthy diet can lead to a risk factor for death pretty much globally. And it tends to disproportionately burden populations that are historically marginalized. So this can be, again, based off of many of the factors that I spoke of in I think on the second slide, race, ethnicity, class, social network, and things like that. All of those things are going to determine the type of food that you eat. How I ate as a single person is very different than how I eat now that I have a family of 4. Yes. Okay. So when we look at dietary intake, what do those survey data look like? So it usually can come into 2 different forms, 2 popular forms. There's about 4 different forms, but food frequency questionnaire. So here, what I'm going to do is I'm going to say, okay, over the past year, how often did you eat this set of foods, right? So the consumption levels are going to be ranged ordinally. So we're thinking about ordinal data. And when we think about that dimensionality, we're thinking about all of the subjects that have been given this survey. How many foods are we querying on? And then how many levels? So in those 3 dimensions, that can come to be a really, really large number. Similarly, if I'm looking at 24-hour dietary recalls, now I'm also concerned about the amount of consumption, because now I can say, tell me everything that you ate within the last 24 hours. And since I'm asking in the last 24 hours, your recall should be a little bit better to tell me whether you finished the whole hamburger or if you had a half a hamburger. So things can get very, 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 very granular, because you can have something as very specific as I had a McDonald's Big Mac and a Diet Coke supersize versus I had a Morningstar veggie burger. So oftentimes what happens is we'll summarize these into major groups just to kind of control the scalability. I remember my first data set with dietary recall had over 16,000 food items. Very cumbersome to analyze, so we had to kind of dice that down and find ways to group those foods together. So once again, when we're talking about the dimensionality, how many subjects have been queried, how many foods or nutrients were reported when they talked about what they ate, and then the amount of consumption. Okay, so how can we use this Bayesian mixture model for survey diet data? So I'm going to talk about 2 recent approaches that we've created. There's an unsupervised approach, which basically means I just want to look at the dietary intake. I just want to look at the exposures, try and understand those patterns. Whereas in a supervised approach, I want to understand these exposures, but I'm really interested in how those exposures might depend on a specific outcome. So the first we're calling is a weighted overfitted latent class analysis. So this is basically, we're going to use the Bayesian mixture model structure, and then we're going to extend it to be able to apply for survey diet data and be able to use a lot of that sampling strategies and incorporate that into our estimates. And so our population for that project we're going to look at is diets in low-income adults. And then we're going to switch to a supervised weighted overfitted latent class analysis, where now I care about the diet, but I want to know diet that's dependent on different hypertensive outcomes that I might exhibit. And for that, we're going to focus on low-income adult females. Now, why are we focusing on these? As I mentioned, income, which we're defining as at or below income, as we're defining as at or below the 130% poverty income level, is often underrepresented in a lot of studies, and a lot of cohort studies just doesn't have the data on it. However, we're fortunate to have public access data to the National Health and Nutrition Examination Survey, where they really go over and beyond to try and capture a lot of those different populations that are underrepresented. So low-income adults is one of those populations that they do oversample when they're trying to collect data. And then for the second project where we're looking at hypertension, we're focusing more on females. And part of the reason with that is a lot of the clinical research is dominated by men. And so with this, with hypertension being such a primary diagnosis, there happens to be a greater burden on women compared to men due to the fact that there's just under screening. A lot of men are chosen in clinical trials, and therefore you're making a lot of inference based off of male health when female health is very, very different and our bodies operate very different. And oftentimes things get misdiagnosed. My little fun fact I remember learning about was that a lot of women did not know that they were having a heart attack because the pain that's associated with the heart attack is very similar to the pain that they experience with monthly menstrual cramps. And so because of that, they oftentimes didn't know that they might be having a heart attack or something of that nature. So from this, we're going to be working with 24-hour dietary recalls. I told you this can be very granular. We've gone ahead and reduced this down to 29 food groups, and we'll talk about that soon. Okay, so reminding again the schematic we had before, we were looking at categorical data and we saw that it was ordinal. So we're going to be looking at a multinomial distribution. So what is this going to look like? So once again, remember we had the two parts, the probability that you're going to have a pattern assigned. So this was my probability of Zi equals H. I've now replaced this with a pi H. So some Greek letters up in here. And then for the second part, I mentioned we have a multinomial distribution. So I have what's called a theta, and theta is going to tell me the probability of consuming a food at a specific consumption level, given I look like pattern H, right? So I'll have my observed food consumption, which will be with Yij. So I is going to index each individual. J is going to index each individual food, and we'll have P total foods, and each of those food items will have D consumption levels. And then, of course, reminding again our Zi equals H from before, this is just going to tell us which pattern that we have been assigned to. So both our pi and both our theta individually can sum up to 1. So, of course, you can only have a finite number of patterns. So there's going to be a probability that you'll have one of those patterns. All of that will sum to 1. Similarly, for each food item, you could only have D levels, right? So the probability for each of those levels is going to also sum to 1. Now, oftentimes when we're looking at data, we have no idea how many patterns exist. So this is where a Bayesian nonparametric extension can come in handy, because instead of having to run, let's see what it looks like at 2, 3 classes, 4 classes, 5 classes or patterns, and then you have to run some likelihood information criterions, maybe like the AIC or the BIC, figure out which one is the best model fit. And there's a little bit of a balance, because oftentimes the more data you have, the more greedy they are. And so they want to have more and more and more clusters and more and more and more patterns. So what we can do instead of running, 7,000 or 100 different models, we can just run one model. And so what happens is this K, instead of defining, I know what K is, I can use either an overfitted finite mixture or a Dirichlet process, which is basically the asymptotic parallel. Basically, I'm saying there's an infinite number of patterns that I think exist, or a really, really large number that's so unreasonable, I know it's actually not going to exist. And so what happens is, as I'll go through my MCMC sampling, those empty clusters will just fall out, and the people will be shuffled into some of those non-empty clusters. And so I'll have a finite number once I get to the end. So how do we translate this for survey data? Well, if we rely on the weighted pseudo likelihood approach I hinted at before, we can use a framework that was developed by Kunihama. And so basically what's taking is, this was our likelihood that we've had, and we've kind of upweighted it for each individual based off of the weight that they were chosen to be selected into the study. I'm going to add this normalization constant of kappa, and that's just going to help to adjust for the sampling variability, because the sampling that existed in 2011 could have been completely different than what's within 2012. And so we want to be able to capture the differences in those variations. So how would this look like when I'm estimating? Well, remember, I have a pi vector and I have a theta vector, and both of those need to be estimated, and they both belong to a multinomial distribution. So those that are familiar with Bayesian estimation, I can use a conjugate prior of a Dirichlet distribution to estimate both parameters. So in that case, what typically would happen, let's ignore the part in red, is each of those little buckets. So we'll focus on pi where we're talking about each of those patterns. As I'm going through my MCMC sampler, each of those buckets are going to fill, and the weight is going to adjust based off of how many people are already in there, right? So if I have 500 people that are assigned to pattern 1 and 500 people that are assigned to pattern 2 and 0 to pattern 3, my weights would look accordingly of maybe like 50%, 50%, and then 0 in that third bucket. But now, because we have survey data, we can now use the individual survey weight of inclusion for each of those individuals and then add that in. So what's basically happening is now, instead of the patterns growing by how many people in our sample are in there, now it's based off that weighted population, right? So maybe I am someone who was undersampled and I have a weight of 2. So instead of counting as 1 person in this bucket, I would now count as 2 people. And so that's where the weights come in. And so you're going to do the same thing with your distribution at the food level with our theta. So in the same manner, those that did not consume the Morningstar veggie burger will then contribute to that first bucket of no consumption, whereas those who did eat them every day maybe would then add a weight into that specific level as well. Secondly, what we want to do is, as I mentioned, the more data, the more greedy things become. So this alpha is going to control how big and how quickly new clusters are going to form. So oftentimes what we will do is we'll have a sparsity inducing prior. So we will set this alpha, which is our hyperparameter, to something very, very small. So maybe it's 1 over 100, maybe it's 1 over the number of sampled participants you have, something very small to kind of slow down the way that new clusters are going to grow. Okay, so here's some results. I don't expect you to be able to read all this, but essentially what we've done is we've made a little bit of a bar chart. So we have the 29 different foods. Blue is representing the probability that you do not consume the specific food, given you're in this case, dietary profile 2. Red is going to indicate a low level of consumption, yellow is a medium level, and purple is a high level. So what we saw from this low-income adult population is that there was a general consumption of refined grains, oils, solid fats, and added sugar. This is basically very consistent and in accordance with a lot of what we have seen in previous national diet studies. 2 of the patterns, so this first one and the third one, showed little to no fruit or vegetable consumption. Patterns 2 and 3, if I were to highlight those with potatoes, cured meats, oils, solid fats, and sugars, they had a higher probability of consuming those foods over other foods. Pattern 4 was one of the most distinct patterns that we found in the sense that they had a high legume consumption that was not prevalent in any of the other profiles. And then lastly, pattern 5 looked very similar to pattern 1, but there was more intake of fruits and milks that we didn't see. And if you want more details, you can follow the blue box that has a more thorough discussion of these different patterns. Okay, shifting gears to the supervised weighted overfitted latent class model. Now again, remembering we have our multivariate exposures and we want to link that to an outcome. But with this now comes 2 challenges. One, we need to account for the variance estimation, right? So oftentimes what happens is we want to avoid undercoverage of our posterior intervals just in the way that things are forming. So we can make a post-processing adjustment to recover the sandwich form of this asymptotic variance. And then we can also adjust for clustering and informative sampling to be able to make sure that our variables are associated specifically with our outcome. And part of this variance estimation is all coming into the fact that what we've now added into our exposure is an outcome probit model. Let's see. Okay, now you can see my mouse. I realized I was on the wrong screen. And then also we need a new coding screen to allow for the inclusion of additional covariates. So something that's very common with all mixture models is a thing called label switching, right? So what happens is as you're going through your sampling algorithm, you might be labeled a 1 and you might be the diet that is the vegan diet, right? But then in the next iteration, things reshuffle and the vegan diet's still there, but now it has a new label of 3. And so once you're doing the post-processing, if you were to think, oh, vegan has to be in the first one because I saw it there in the first iteration, you'd be messing up your estimates because you need to be able to follow where does the vegan diet move as it's going through the sampling algorithm. So If we're doing a regression model, if you're just looking at the diets, again, it would just require a reshuffling. But now if we have different covariates, it's messing things up because those covariates oftentimes have a reference cell. And if, again, that first pattern is changing its identity, your information on your estimates is also going to change. So we need a new coding scheme to adjust for that. So as I mentioned, now we've split our mixture model. So we still have that same original latent class model that we talked about before, but now we've added a joint. So we've added the outcome probit model. So in this case, the probability that you observe a binary outcome, either 1 or 0, in this case, it's going to be hypertension. And then you'll have your regression model. So in this case, VI is going to be our individual observed covariates. And then our psi is also going to be our fixed effect covariate that goes with it of our estimate that we're going to be trying to estimate. Okay, so how do we estimate this? Well, Albert and Shiv gave us a very clever way where if we introduce a new latent variable to map the binary distribution to a Gaussian space, we would have a much easier and computational time mapping this and being able to estimate. So essentially what happens is instead of having a 1 or a 0, what I've done now is I'm going to take the Gaussian curve and I'm going to cut it in half. So any value that is negative, I'm going to call that basically the case where yi equals 0, and anything that is positive, that's going to map onto yi equaling 1. So in that case, what's happened is we've added in this zi. So now I've just expanded this Gaussian distribution, and I still have my vi, and that's just going to kind of show how things will shift based off of this now Gaussian distribution. The second part, we talked about dealing with the variance sampling. So what we'll do is we can add a pseudo posterior that's consistent under a complex multi-stage sampling design. So remembering before how we had our likelihood and we kind of upweighted it with the weight, we're now adding an additional factor to be able to adjust for consistency as we're going through, since now we're using a regression model on top of our latent class model that we introduced. So we can plug in weights. Our plug-in weights oftentimes will exhibit under coverage, so we need to do a post-processing adjustment. So in this case, we're going to recover the sandwich form of the asymptotic variance based off of that pseudo likelihood that we talked about before. So we'll use the variance associated with that pseudo likelihood and do the sandwich. And this will help adjust for the clustering and informative sampling. Okay, so the sampling adjustments we have our Gibbs sampler, which I talked about. And so once again, like we have our patterns, which are pi, our theta, which is describing, our distributions. And then our xi is going to be those fixed effects that are related to our regression model. And so those are just going to go through the same conjugate priors of a multivariate normal or a normal inverse gamma. Multivariate normal would be the normal mean as well as the Wishart. Then for our label switching, we'll adjust for label switching using a hierarchical clustering to find individuals who are likely in the same class and adjust their labels throughout the MCMC. Basically, what's happening here is I want to know if 2 people were clustered together in iteration 1, how many times they stayed together as they went through the MCMC. And so I'll make this giant n by n matrix that's going to kind of tell me who gets clustered together, and I'll form my clusters that way. And then we now need, I mentioned a new sampling scheme or a new coding scheme for our regression. So what we can do is we can have interaction effects. So we're going to separate our regression coefficients for each latent class to allow for class covariate effect modification. So essentially we'll have an interaction for each of the individual classes that we have, and that's going to be separate from what we do when we look at our regular regression coefficients. So it's almost going to be like a mixed reference cell coding. So as I mentioned, we looked at this for diet hypertension patterns of low-income adult females. When we did this, we found 5 patterns and we were able to give them a name. So the first one we called multicultural. So here we see a higher intake of oils, nuts and seeds, organ meat, other starchy variables, dark green vegetables, and other fruits. Health American, we see our dairy, again, some more organ meat, whole grains, which was really important, and then some other red and orange vegetables. Our Western style diet, had more of our poultry, our refined grains. And then we had a restricted vegetarian, where basically similar to what we saw, where essentially it's just a lower consumption of what we saw under the healthy. And then the same thing with restricted American. We saw lower consumptions from what we saw from the Western. And of course, all of these diets were adjusted for age, race, ethnicity, smoking, and physical activity. So just to highlight, and this kind of also shows some of the motivation behind some of the names, we called that first group multicultural, as it had the most non-white participants that were assigned to it. So for example, we saw 20% of the non-Hispanic Asians were assigned to that pattern. The healthy pattern we found was more prevalent amongst younger participants, so those that were aged 20 to 40. The restricted vegetarian group, of those that were identified as either an other or a mixed race, they had the highest prevalence within the restrict vegetarian, and then the restrict American, they were more likely to be active, so about 58% of them. And then we can do a couple of different plots to try and understand what's happening in this relationship of the dietary pattern and as it relates to the probability of hypertension. So one thing we know when we're looking at things by age, as well as by race and ethnicity, those that were in that restricted American diet had a higher proportion of people that identified with hypertensive outcomes. And they were also more likely to be inactive physically. And then as far as on the lower end, we are seeing basically that multicultural diet for when we're looking at things of age, as well as smoking status and physical activity. So if you're interested in implementing either the unsupervised or the supervised version, we are in the process of getting it on CRAN, but there is an R package available called Basic. You can find the GitHub link here. Basically, the unsupervised link, you can use the WOLCA. There's a function for you to be able to adjust for the variance. And then if you're interested in doing a two-step approach, so I introduced the supervised as one step, you could do a two-step. So let's say, for instance, you just want to see how diet looks or however your exposure patterns look, but then you want to fit it with a bunch of different outcomes and just see how they fit. You might choose this two-step approach, in which case you can use the WOLCA, and this kind of merges with the GLM package. Again, for the supervised, you can use the SWOLCA package. And then one thing to note, sorry for this typo, if say you don't have survey data, let's say you have just a regular cohort study, but you do want to still implement this overfitted latent class model, if you set the weights to 1, then it'll look just like a regular overfitted finite mixture or a regular supervised overfitted finite mixture. And so that's great, because if anyone has tried to look for latent class packages in R, you're a bit limited. So there's the POLCA, which basically does the frequentist version, where again, you'll need to specify what your K is and run multiple models and use either like a BIC or an AIC to determine the best fit. And then there's the Bayes LCA, but that's limited to binary data. So the basic package allows for you to have multivariate categorical data, so you could have more than 2 levels for each of these consumptions. And I'll pause right here if there are any questions. Okay, I'm going to keep going then. All right, so now we're going to switch gears and talk about mixture models for binary data. And this was mainly applied to form a framework for social determinants. So how can where you live influence a facility's adherence to evidence-based guidelines for treatment? So the census collects neighborhood social determinant data, and it's captured at the census tract level. So there's many different ways to identify social determinants of health. And one of the things we've noticed is that these things are highly correlated. Oftentimes what we have seen is when you're looking at how you want to define maybe socioeconomic status, they might choose 1 or 2 different variables. Maybe they'll look at education and income, but we feel like it's a little bit more complex than just education and income. And while you could make a nice little interaction variable between those 2 things, if you go through the census and all the different opportunities that could determine someone's health, the list can get longer and longer, and no one wants to have this like 12-way interaction variable in their regression model. So we can use a mixture model approach. So this figure to the right, get on the right screen. This figure to the right is basically showing you the variables that we've used, and you can see the levels of correlation that these variables have, such that we do need to have to capture all of that information together, that relationship together, excuse me. Okay, so we can use what's called a multivariate Bernoulli mixture model. So once again, remembering we have that pi k, and that's just going to tell us what pattern we have, or in this case, what is the profile based off your neighborhood social determinants that we're going to put you in. I can have my list of indicators. So again, J is going to index each social determinant that I've included into my model, with P being the max. And then I have my Bernoulli distribution, right? So you'll have the probability that you have a high exposure of this variable, or the probability that you have a low exposure of this variable. In this case, what we did is we used the population median. So if you were above it, we considered that high, and if you were below it, we considered that low. So with that, now we did a different approach. We're trying to figure out how many patterns. We basically put a prior on the number of patterns. So we fit K to come from some sort of discrete distribution. This could be a uniform, it could be a Poisson. And then once again, we have our pi given the number of clusters. So that's going to be that Dirichlet distribution. And again, for those that are familiar with Bayesian methods, the convenient conjugate prior for a Bernoulli distribution is a beta distribution. So you can use what's called the Bayes-Bin mix R package, and this is a model-based clustering approach for multivariate binary data. Basically, this K, they use a metropolis-coupled MCMC to determine the number of patterns. So we wanted to use this specifically to identify neighborhood social determinants of health profiles in Massachusetts. So we selected 16 neighborhood social determinants from the census, and we summarized these into 4 domains. So we had variables that were considered housing conditions and resources, economic security, social and community context, and then educational attainment. So each of these variables, if you look them up in the census, they're represented as proportions or percentages. And so we basically converted that over to a Bernoulli, again, using that median. And the reason we felt okay doing this is because oftentimes there can be a loss of information. There was minimal loss of information just due to the sparsity in the way that the data looked specifically for Massachusetts. So we got the state level median for each of these different variables. And then again, as I mentioned before, if it was above it, we considered that a high exposure. And if it was below it, we considered that a low exposure. So here's our pipeline. We took our data from the census, transferred it over. We created our neighborhood profiles. We ended up with 8 profiles. And then what we wanted to do is we wanted to see how these different neighborhood profiles might relate to different cancer outcomes. Specifically, we were concerned with gynecologic cancer or endometrial cancer in this case. So we looked up what is considered the optimal care that the National Comprehensive Cancer Network guidelines specify. And basically, patients that belong to these different that lived in these different residential profiles, did they receive that optimal care or not? And then we also adjusted for clinical and sociodemographic variables. So this is work that I did with my student Carmen Rodriguez Cabrera and with Dr. Alamina, who is the expert in OBGYN cancers. So in our results, I'm not going to go through all 8 due to time, but I will highlight the first 2. So up top here, this was our largest profile. And so you'll see here, it had a high proportion of neighborhoods that were owner occupied. So they owned rather than rented. They had an income above the state median. And also in pink, you can see they had a high proportion of high school and college educated residents. Profile 2, this was considered our most deprived set of neighborhoods. So in this case, what we have is they are mainly renters. Many of them do not own a vehicle. There's limited English proficiency. Many of the homes have a female head of households. There's a lot of household crowding, excuse me. And as mentioned right here, most of them have less than a high school education. If you're curious to see how this shakes out for the whole Massachusetts, we've created a Shiny app. Is the QR code on here? Yes. So you can use this QR code to kind of hover over different areas of Massachusetts and see how the different profiles might look. As might one expected, if you are familiar with where a lot of the colleges and universities are, you're going to see a spike of educated residents over there. And if you're familiar with some of the rural areas, you'll see areas where there might be, again, more owner-occupied housing. There's some areas that don't have sufficient plumbing, things of that nature. Okay, pausing again, checking time. Okay, I'm going to keep going. So now we're going to do a combination. So a mixture model for normal and categorical data. So in this case, we're going to look at normal data as well as multinomial data. So we're going to do this in two parts. So first, we're interested in looking at a Gaussian mixture model for environmental mixtures. So looking at multivariate normally distributed data. This specifically because we want to get a better understanding of how the combination of current and new environmental exposures, specifically, PFAS, may have on your health. So PFAS, of course, is not normally distributed, but if you log transform it, then it looks very normal. So that's kind of how we were able to use this. What's happening again, I've switched up on you guys. So instead of that pi, I've replaced it with a W. So that's going to be the probability that you're going to have, some specific PFAS exposure profile. And then of course, you'll have your multivariate normal distribution where the set of different PFAS variables will be summarized with our mu, our mean vector, and then of course, our variance structure, which will be a matrix. And then my observed PFAS exposure variables will be described with xi. Sorry, just checking the chat. Oh, thank you, Leandra. So our clinical motivation. So PFAS are hydrophobic, lipophobic, heat-resistant chemicals. PFAS exposures oftentimes may be linked to several severe health effects. Standard methods tend to look at just one PFAS exposure by itself individually, or they will look at it jointly, but they'll just look at all of it combined. It's not really giving us information of, oh, the PFOS is really high or the, PFDA is really high here. It's just all of them together. We're not quite sure how each individual PFAS exposure is contributing specifically. Secondly, we want to look at the relationship of PFAS and diet. So I say that because ways that I can be exposed to PFAS is by eating fish caught from water that's contaminated with PFAS. The food packaging can contain PFAS. And then, of course, the water, whether you're private well water, it could be contaminated. And if you're using that for cooking and any other purposes, you would be exposed to PFAS as well. So here we use what's called a Bayesian repulsive Gaussian mixture model. So I briefly hinted earlier about the Dirichlet process and the overfitted mixture model where I don't know how many patterns exist. So I just throw a really, really large number or just call it infinity and let the sampling do its magic and give me the finite number at the end. The problem is oftentimes it requires a lot of post-processing because oftentimes you can get a lot of redundancies. You might get some really small clusters that might be significant, or maybe they're just noise. There's no way to really decipher between the two. And this is basically because we're putting independent priors on each of the mean and variance vectors that we're having for each of those specific clusters. So the Bayesian repulsive Gaussian mixture model, basically what it does is it introduces a repulsive prior to each of those mu's and sigmas to be able to encourage those clusters to separate apart and be able to improve our identifiability. So we're going to introduce this variable called G0, which is going to control our degree of repulsion. So if I look over in this blue box, basically what I have is I have this H function, and this is going to be my repulsive function, and it's going to penalize clusters that are too close together and force them apart. Everything else is going to pretty much stay the same. I'll have my usual base priors, and then I'll have a normalizing constant so that everybody's a happy family at the end. And this was first introduced in a JASA paper with Yanwan Ju and Jai. The second part is we wanted to care about diet. So if I use the Bayesian repulsive Gaussian mixture model to create these exposure profiles for PFAS, I can almost consider them as different subpopulations. And so now what I want to know is how is my diet different because of this subpopulation or this PFAS exposure profile that I belong to? So traditionally we talked about this mixture model in the two parts. What the caveat is if I'm talking about diet, what I'm saying is, okay, if you're in this specific pattern, then I'm expecting that every single person is eating all of the same foods. But in this case, when we're thinking about PFAS exposure, sometimes, maybe I'm using different packaging from someone else. And so therefore I might be exposed to PFAS differently than someone else. So maybe, yes, we both had beef patties, but because my beef patty was packaged and I bought it at the grocery store versus this beef patty I bought at the farm, we're going to have different, we're going to exhibit different exposure profiles. And so with that, I want to break apart this assumption. And so what's going to happen is I'm going to break this into two parts. So now I'm going to say, okay, what are the foods that basically everybody's eating? And what are those patterns? So I'll describe that in the blue box. And then the second is, okay, based off of the fact that I'm from this specific PFAS exposure profile, how might my diet be different from what I just described in that blue box? And so now I have what's called a local profile, and it's going to be based off those PFAS exposures that I defined. So I'll have a whole different mixture model just for all of us that are part of this smaller subpopulation. So I'm going to be looking at three parts. So one, what's the probability that I have this overall pattern? So my global cluster membership, which is pi. And then let's say I belong to a specific PFAS subpopulation. What is my dietary pattern going to look like in there? And then as I'm looking at all the different foods that I'm defining with the diet, which of those foods should be classified with the blue box and which of those should be classified for the yellow box? Meaning, which of these are a shared pattern that basically everybody's doing regardless of the PFAS exposures that they have? And then which ones are very specific to the fact that I had specific PFAS exposures that were really high, and therefore my diet's going to look very different. So when I'm thinking about estimating this, now what I'm going to do is, just as before, I'll have my Dirichlet distribution. So I'm going to use that overfitted mixture structure. And I'll do the same thing globally as I will do locally. So everything's going to look exactly the same. But now, now I've added this split, right? So now I have this deviation indicator. So what I need to do is all of the individual foods that I've had to define my diet are now going to have to make a decision of whether they're going to go global or they're going to go local. So I can use this with the Bader-Bernoulli process, right? So GIJ is going to define, yes, I'm going to go global, or if it's 0, it'll say, no, I'm not. And it'll be defined by the probability defined by nu J, which then can be governed for each specific subpopulation. So each specific subpopulation will have its own decision-making process. So if you're interested in playing around with some normal data that you have, multivariate normal data that you have, and you want to be able to have great separation, it's not an R package, it is on MATLAB, but they do have the code available through their JASA paper, so you can follow this link here. The RPC that we've used, there's two versions, a MATLAB version, which can pair with the BRGM that I just discussed. But we've also done an R implementation, which is in the process, again, of getting put onto CRAN. So you can follow the GitHub file here. And once again, there is a weighted extension for those that are dealing with survey data. So once again, if there's no survey data, you can just have the weight equal to 1, and you've got your regular RPC. If you want to use the weights, it can be incorporated there through that GitHub link. So we use this Project Viva participants to look at pregnant women that were enrolled at the first prenatal visit, collected data from 1992 to 2002 in Eastern Massachusetts. So we had 8 PFAS measures. We only did 6 of them because 2 of them were just very, very small and below the levels of detection. And then we had a food frequency questionnaire of what did they eat while they were in their first trimester of pregnancy. So we have 158 food items there, and then we've got some demographic data. I know I'm running short on time, so I apologize. So here you can see kind of how the differences of the PFAS exposure subpopulations. So these are my 6 PFAS exposures, which are listed below. And then each of these different box plots is showing the range that we're seeing with each of the clusters. So we had 6 different clusters. Our largest clusters were clusters 2 and 3. And our smallest clusters were clusters 4 and 6. So shifting, how do these things account for the different subpopulations? So first, I'm just going to focus on the overall the overall dietary patterns. So we had 5 overall dietary patterns. Profile 1 had higher intakes of caffeinated beverages, added butter and margarine, ice cream and cookies. Profile 2 had decaffeinated tea, garlic, wine, etc. Gonna skip around a bit. Global Profile 5 had a lot of sugary sweetened beverages, chicken, white rice, and red meat. So then where things get flipped is now we're going to think about each of those 6 subpopulations and how might foods deviate or differ. So we use a conservative threshold. So basically anything that had a probability of 45% or higher, we signified that as a global pattern. And anything that was below it, we signified that as a local pattern. And that was just more for us to explore and understand where differences may lie. So when we use that threshold, we found that 110 of the food items preferred to do something locally, right? This doesn't mean it was doing something locally for all of the different populations. It was just for some of the subpopulations. So you'll see in this figure to the right, because again, I'm running on time, so I'm not going to go through everything. The gray squares mean for that subpopulation, it wasn't doing anything locally. You can just follow what you saw in that global pattern. But for those that are colored, we can see that there are changes. So like one thing I'll note here is for those that are in subpopulation 4, regardless of what pattern you saw at the overall level, we are having a much higher frequency of consuming garlic compared to any other subpopulation. So that's pretty much all I have time for. We are still working on other data to look at ongoing work. So we've got a Poisson distribution where we're looking at food establishment profiles in colorectal cancer hotspot regions. So basically, if I were to look at that neighborhood, similar to what we did with the neighborhood social determinants, but now I'm looking at the number of fast food restaurants, the number of convenience stores, the number of grocery markets, the number of farmers market, things of that nature, to kind of create a profile of the different resources that residents have for food. We're looking at a beta distribution now where some of our census data we're able to find have aren't as simple to just kind of binarize. You really want to capture a lot of that variance that's happening. So trying to look at how we can mix up data from the census to look at bounded continuous data. And then lastly, a lot of this data has been looked at things cross-sectionally. We're moving more into a longitudinal space, in which case, what if instead of using these traditional probability distributions, we looked at regression models? So we're looking at ways to look at longitudinal phthalate and principal care product use patterns, as well as longitudinal dietary patterns. And I am running on time, so I'm going to pause and get to the end.
Thank you so much. But, it was a really excellent talk. I think there are a couple of questions in the chat, but it's also lots of praise in the chat. So feel free to browse them. I'm going to just ask if anybody has a question that they want to come and ask in person. Otherwise, I can pick one out of the chat, but feel free to raise your hand. We'll have time for 1 or 2. And if nobody wants to say it in person, I will just, I don't know if you can see Chris Newby's question in the chat, Brianna. I don't know if you would be able to address that.
Okay, so it looks like they want to compare the weighted to the unweighted. Yes, so if you read the papers, we did a simulation where we basically compared our results with the unweighted version. Basically what happens is your patterns in some cases look very different. And that's basically because when you're looking at the unweighted version, if I had an oversampling of a specific demographic and it's driving a specific pattern, it's going to overpower and dominate that pattern being displayed. Whereas if I'm using the weights, so like, for example, the oversampling of low income, but if I looked at the regular sample, it might not look that way. So I'm able to capture more of the true pattern identifiability. And it also messes up the coverage as well. So there's some plots in the paper if you wanted to follow to see how that happens.
Great, thank you. Someone has also asked that they really liked your Shiny app, and I don't know if your code is available on your GitHub for that, but somebody has requested any resources for the Shiny app.
Wait, what's the Shiny app question? I missed it.
I think it might have been the one that was the map of Massachusetts, but please feel free to correct me, Justine, who's asked the question.
Yes, she had created a Shiny app, and then so I wanted just to know about the creation. I've created like very simple ones, but I'm thinking this looks like very sophisticated, so I would love to just have a look.
Yeah, I can connect you with my student who created
Okay.
the Shiny app, and she can
Okay.
help with the code for you.
Thank you. Thank
Mhm.
you.
Thank you so much. Just to say that the session will be shared online, and it's recorded, so you can come back and have a look at it if you kind of want to refresh. But yeah, in the interest of time, I would just thank you again so much for being our speaker today, Briana, and it was really interesting. You always want like more time to actually like be able to discuss everything. But yeah, thanks so much for joining us.
You're very welcome. I
Yeah,
did
it was
see
a pleasure
Chris's
to
second
actually-
follow-up question, I think,
Yes.
about the truncation. You end up with a small number just because of the sparsity prior that we've induced. So, but how you define that truncation can vary. So I think at one point I did it at 50, and then another one I did it like 30. So, but yes, it will make a difference in your processing time.
Thank you. Really loved the presentation. It was brilliant.
Great. Thank you so much, everyone. Thanks for joining, and hopefully see you at our next webinar, which is in early March, and you can sign up on our website.
Thank you all for having me. Take care.
Yeah, Brianna, I've shared my email directly to.
Oh, yes. Let me link it now so I can email you.
Thank you.
All right.
Bye.
Thank you. Mhm. Take care.
Thanks.